Okay, so we're doing this next problem here. For every pound of methane, how many pounds of air is required? And so for this, we don't need to split it up into half reactions, we'll just balance. But we aren't going to balance by ions like we did the last problem. What we're going to do is we're going to balance by atoms. And we always save oxygen for last because oxygen only consists of one element. Everything else consists of two, sometimes more elements, but two elements. So if I change this, this impacts both carbon and hydrogen. If I change this, it only impacts oxygen. So save that for last. So over here we have one carbon, here we have one carbon, so the carbons are balanced. Here we have 4 hydrogens, we only have 2 hydrogens here, so I'm going to balance it by changing the coefficient. Here we change the coefficient, we don't add, like we did earlier, we just change the coefficient. And so the balancing scheme is quite a bit different than the skeleton redox. Skeleton redox is very specialized. You only do that. I'd never add H+, If I'm missing hydrogens here, I'd never add H+. If I'm missing oxygens, I'd never add water. I just balance it by changing the coefficients. And so keep that in mind. Skeleton redox, you play by a different set of rules. And you have to use that set of rules in skeleton redox. And so what most people do with skeleton redox is they just remember the rules. After you do a few of them, it's easy to remember. Okay, then that balances that. That gives us how many oxygens on the right? We got 2 plus 2 gives us 4 oxygens. On the left we have 2, so we need 2 here. And now it's balanced. So we have methane gas plus oxygen gas yields CO2 gas. Water is a liquid here. So this is the same for both problems here. We need to balance the chemical equation that tells us the stoichiometry. This is called the stoichiometry, that is the mole ratio of it, or the quantity relationships. So at the heart of the stoichiometry map is we want to do this. We want to do a conversion from moles of methane, because that's what we're given, over to moles of, well, what can we relate it to? Moles of O2. But moles of O2 is fine, but air is not pure O2. Air is a mixture. And we're going to assume that air is 80% nitrogen and 20% oxygen. It's not entirely accurate, If we wanted a more accurate composition, we could look it up. In fact, did earlier. So let's take a look at the composition of air here. So if we go to Wikipedia, they say by volume, dry air contains 78.09% nitrogen, 20.95%. So it's closer to 21% oxygen. But we're going to ignore all the other components. So it's almost 1% argon, 0.04% carbon dioxide, etc. And we can't forget about humidity, water vapor and air. And the humidity changes depending on it. So we need to know the humidity in order to figure out the percentages correctly. Since the mixture changes a bit, I'll just use these very rough approximations of the composition. So we'll ignore the minor components. Now, is that a percentage by mass, or is that a percentage by mole? What do you think? It's very important, because what does that mean here? Well, it says by volume. But let me tell you this. If it's a mass percentage, then it would be 20 grams of O2 for every 100 grams of air. So it would be fine. However, if it's a mole percentage, then it would be 20 moles of O2 for every 100 moles of air. So which one is it? Is it a mass percentage or a mole percentage? It's hard to tell, unless they tell you. And so I'm going to tell you it's not a mass percentage, it's a mole percentage. All right, if it's a mole percentage, then we can relate moles of O2 to moles of air. So if we know how many moles of O2 we have, we know how many moles of air we're going to have. And so this is our map. This is the center of the map, and we always want to go to the center of the map here and then make our conversions. And so what we're going to do is we're going to start off with pounds of methane. And from pounds of methane, we'll go to grams of methane. And then from grams of methane, we'll go to moles of methane, because we know the molar mass of methane. Okay, so once we're at moles of methane, then we're here. So we can go from moles of methane to moles of O2. It's a 1 to 2 mole ratio here. And then once we're at moles of O2, then we can relate that back to air, because it's 20% by mole O2. And so what that means is for every 20 moles of O2, I have 100 moles of air. And so we're going to go from moles of O2 to moles of air. And then from moles of air to grams of air. But we're going to run into trouble here in going to grams of air. Because in order to go from grams to moles, or moles to grams, we need the molar mass. The molar mass is just the ratio, grams to moles. So here, gram to mole conversion, I need the molar mass. Mole to gram conversion, I need the molar mass. Well, the molar mass of methane is not so hard, because carbon is a 1201. We have 4 hydrogens at 101 each, so it would be 404. So it's 1605 grams per mole for methane. But what about the molar mass of air? What is the molar mass of air? That I'll have to figure out. Then once we're at grams of air, we go to pounds of air. And so the first problem we have to deal with is what is the molar mass of air. So if I have a mole of air, I'm going to have 6.022 times 10 to the 23rd air molecules. 80% of those molecules will be nitrogen, 20% of the molecules will be oxygen. If I have a mole of oxygen molecules, it weighs 32 grams, 16 times 2. If I have a mole of oxygen, then it would be easy, but I don't. I have a mole of oxygen and, well, actually, I don't even have that. What I'm going to have is a mixture. And so what is the molar mass of air? Well, the molar mass of air can be determined by this. It's just the average mass. Now, what is the average mass of a molecule of air? Do you know what it is? Well, it's the same type of question as what is the average mass of an atom? Well, the average mass of an atom is a weighted average of all the isotopes that it contains. And so, for example, chlorine, 75% of the chlorine weighs 35 chlorine atoms. 25% of the chlorine atoms weigh 37. And so if 75% weighs 35, 25% weighs 37, then the average mass is going to be 35.5. Do you remember doing a calculation like that? That's for the atomic weights. So we're going to use the same equations as atomic weights. So the average molar mass of air, since air is a mixture, and atomic weights are mixtures of isotopes, we do the same thing. So 20 out of 100 molecules will weigh 32.00, O2, 2 oxygen, 16 times 2. Plus 80 out of 100 will weigh, well, what does nitrogen weigh? Each nitrogen is 1401. We have 2 nitrogens, so it's going to be 2802. If this were 100% oxygen, then the molar mass would be 32. It'd be 100 over 100, 0 over 100. If this were 100% nitrogen, it would weigh 2802 because there'd be 0% oxygen. And so do you remember doing something like this way back in isotopes? Yeah. And so we're going to do this, and we're going to get, well, what are we going to get? Let's see what it comes out to here. .816. Now, are my percentages very accurate, would you say? So I don't want to, this would be way too many sig figs. So I'm just going to go with about 2 sig figs. So we'll just call it 28 sub 8. I don't want to round to 29. Maybe I should round it to 29. I don't know. But that's with this composition. If I try to get a more accurate composition, then what would it be? Because I do the same thing. What I did was I did 20%. Well, I should have done 20.95. 20.95 out of 100 would be 02. Put that here. And then over here, this should have been 78.09 out of 100 will be 2802. And then 0.93 out of 100 will be argon. Argon is 39.95. And then carbon dioxide, 0.039 out of 100 would be 4401. Et cetera, et cetera. So if I did that, what would the molar mass be? So we can take a look at the molar mass of air based on this composition. And the molar mass of air comes out to 28.8. Well, this is the average. So just roughly around there, 28.8. This morning I miscalculated. I got 29.4. Screwed up the calculation. But this calculation looks pretty good. Okay. All right. So now we have everything we're going to need to solve this. So it's just dimensional analysis. Normally what you do is you just keep trying to cancel things out until you hit a dead end or you get to the answer. And so I'm going to start off with 1 pound. And since this is a hypothetical problem, I'm going to just say this is exact. Let's just say infinite sig figs. If I burn exactly 1 pound of methane, approximately how many pounds of air is required? And so if I go 1 pound of methane, then I'm going to convert that to grams, 453.6 grams per pound. So pounds canceled, that gives me grams of methane. Well, if I know how many grams of methane, I can figure out how many moles. I have the molar mass there. And so 1 mole of methane molecule, 6.022 times 10 to the 23rd molecules of methane weighs 16.05 grams. And so the grams of methane cancel the grams of methane, that leaves us with moles of methane. So here is where the stoichiometry mole-to-mole conversion comes in. I can go from moles of methane to moles of, can I go straight from moles of methane to moles of air? Well, I have to go there indirectly. I can go straight from moles of methane to moles of oxygen. So let's go here. There are 2 moles of oxygen required to burn a mole of methane. So moles of methane cancel. Okay, now I can go with my mole percent. What was the mole percent? The mole percent is this. For every 100 moles of air, I'm going to have 20 moles of O2. So that's my mole percentage there. And so now I have how many moles of air I need. I just got to figure out how much that weighs. Well, I know how much a mole of air weighs. If I have Avogadro's numbers worth of air molecules, it's going to weigh 28.8 grams of air per mole. And then I'm going to go to pounds. So 1 pound is 453.6 grams. Well, if I look at this equation, I can simplify this. I'm multiplying by 453.6 divided by 453.6, so I'm going to ignore this term. This is just 1 here. So let's do it off the top. I'm going to get 2 times 100 times 28.8 divided by 1605 divided by 20 divided, oh, that's it, 17.94. £17.9, so about 18 pounds of air. So to burn 1 pound of methane requires 18 pounds of air. Does that sound about right? Yeah? This is just a 1 to a 2. Isn't it like this? If I have CH4, I just need 2 O2s. So isn't it, for every pound of methane, don't I need 2 pounds of O2? For every pound of methane, isn't it 2 pounds of O2? So this should be about 2 pounds of air, not 18 pounds of air. Is that right? No, it's not right because, you know, if I have 1 methane molecule, I'll need 2 O2 molecules. A methane molecule weighs 16, an O2 weighs 32. And so if methane weighs 16, O2 weighs, wait a minute, isn't that a 1 to 2? And so if this is 16 grams and this is 32 grams, isn't it double the mass? So for every 16 grams, I'll need 32 grams. For every 16 pounds, I'll need 32 pounds. For every 1 pound, I'll need 2 pounds. Isn't that about right? It turns out no, because 32 would be for 1 O2. How many O2s do we have? We have 2 O2s. And so the mass, it's actually 64 grams. So for every 16 grams of methane, I need 64 grams of O2. And so what that means is I need 64 grams of O2 for every 16 grams of methane, which gives me a ratio of 64 divided by 16 is 4 to 1. So for every 4 grams of O2, I can burn 1 gram of methane, or for every 1 pound of methane, I should need 4 pounds of O2. Now this is not a mass ratio. If I want the mass ratio, I'd have to figure it out like this, which is more of a pain. And it's not necessary to figure out the mass ratio if we use stoichiometry. But anyway, if I burn a pound of methane, I'll need about 4 pounds of O2. Why am I coming up with 18 pounds? Is that right? Yeah, you're right. Because air, it's not O2, it's air. And air is made up of mostly nitrogen. And nitrogen is what we call inert. It's relatively inert. It's not going to combust. And since air is only 20% oxygen, then it does make sense. You know, we'll need about 5 times as much. So 5 times as much would be, 5 times 4 would be about 20 pounds. So this is about right, about 20 pounds of air. Does that make sense? Okay. All right, let's take a break and then start again.